stuff that's shown on that graph. That in an instant, the universe threw at us all the materials, all the atoms needed to build stars and galaxies. And so he assigned a couple of graduate students, at the time George Washington University, compute the abundances based on what is known about nuclear physics, that is, the assembly of the nucleus of various atoms of different atomic numbers by adding neutrons and protons. Let's just calculate the abundances, and students, we should get this curve. We should know how much boron is in the atmosphere based on nuclear physics. And so they did the work and they said, sorry, professor, you're wrong. And here's why. The problem is neutrons. In the early universe, neutrons were produced in abundance. But an isolated neutron is not permanent. It lasts about 10 minutes. Or 9 minutes or 11, what do I have up there? I don't have it. Okay. It's about 10 minutes. An isolated neutron decays into a proton, an electron, and some other debris particles. And they said to the professor, there's the neutrons that were created in the explosion that started the universe. There's not enough of them around after a couple of minutes to actually create heavy elements, because to create a heavy element, again, you need, if you start with a hydrogen nucleus, it's just a proton, you're going to add a neutron and more neutrons and protons and eventually build something heavy, like uranium. But by the time you get there, all the neutrons, the free neutrons in the early universe, would have decayed. Little side note, protons don't decay. Their lifespan appears to be longer. An individual proton will just sit there and be a proton for a time longer than the age of the universe. There's no known event where a proton is decayed on its own. So they went to the professor, had to hold their breath because he could be a fire-breathing dragon. And so the last little thing I just put up is what I just said. There's no known way to build all the elements that are seen in the universe from just the products of the initial Big Bang. Those heavy elements had to be created in stars. Now, here's this little panel I just put up. Let me put it up again so you don't miss it. The most important thing the students found in studying this problem was, A, there were two things. A, professor is wrong, there's not enough neutrons. B, the Big Bang must have produced an enormous amount of electromagnetic radiation. We should be able to see it today. And that's a topic we will come back to over and over in this class. They predicted the cosmic microwave background. This is in like 1948 to 1951. That was not detected until the early 60s. And it was detected by accident. So Gamow, always a character, he wrote this interesting little poem. Twinkle, twinkle, quasi-star, biggest puzzle from afar. How unlike the other ones, brighter than a billion suns, twinkle, twinkle, quasi-star, how I wonder what you are. We now know what he was concerned about. And what he didn't know about, but what was powering these enormously powerful stars called quasi-stellar objects, are black holes. But we'll get back to that. Okay, now, this is a really important chart. Here is the detail about nucleosynthesis in the early universe. So, here we go. Time zero, this is in seconds, so this is 1 second, 10 seconds, 100 seconds, 1,000 seconds. At 1 second after the Big Bang, let me get my pointer, almost all that existed in the universe was hydrogen. Sorry, I should have had this prepared. There. So this chart's a little funny. Right, that little tick mark right there, that's the number 1. So normally in a chart, if it goes from 0 to 1, you wouldn't bother putting this extra business up here. So just try to ignore that. So in the early universe, 1 second after the Big Bang, almost everything in the universe was hydrogen. There were neutrons. The two of them together was everything. But notice what happens to the neutrons. As time progresses, as I said, neutrons decay away. They turn into protons, which are important, but it depletes the number of neutrons. And this is what we call a logarithmic scale. So it's really, if you saw this on a regular graph, hydrogen would have been the totally dominant thing in the universe. This yellow line is an isotopic form of hydrogen called deuterium. There was almost none of that. And that was it. There's 3 things. But if you build a model based on modern nuclear physics of how the universe at very high temperature gradually got cooler and all these particles were banging into each other and interacting, you get this set of curves. So for a long time there was, this is helium. This green line is helium. In the early universe, until 10 seconds, there was no helium. But the temperatures were high enough that protons and neutrons were being thrown together and eventually finding partners with electrons, and gradually we get helium rising in value. And by the time we get here to 1,000 seconds, you see at 1,000 seconds everything is done. That's why Steven Weinberg called his book The First 3 Minutes. Because 3 minutes is kind of like right about there. So this is the theory of how much helium, deuterium, an isotope of helium called helium-3, hydrogen-3, beryllium. Remember I mentioned beryllium and lithium. Notice how everything gets stable here except the neutrons. The neutrons are drifting down. The dotted line, I have to admit, these are isotopic things. Okay, so here's our point. Initially, all we have is hydrogen and neutrons. After about 3 minutes, we got this group of light elements. That's all that was produced in the Big Bang. So I put a little tick mark there where 100% is. Oh, and then I have these things at the bottom, 1 second, 1 minute, 1 hour, 1 day. But in far less than an hour, everything was done. And there's the neutrons I was talking about. So here's the dynamic that goes on. So we have a proton and a neutron. We get a deuterium nucleus. When that happens, a little light pops out, but now we have deuterium. And you bang 2 deuteriums together, you can produce an isotope of hydrogen called hydrogen-3. And now a hydrogen-3 and a deuterium bang together and you get helium. So there's like almost like chemistry going on, except it's happening at the nuclear level. Remember, let me remind you something about the chemistry you had in high school. Chemistry is all about how the electrons change in number and in energy around the nucleus as they interact with other atoms, and you end up forming molecules. This is nuclear chemistry, where we're synthesizing elements, and this happened in the early universe. Okay. Now, here's a point. This is an interesting. Let me check something. Maybe I can. Let me make sure I make the right statement. Yeah. A little hard to see here. It's a little hard on this scale to see. But you see, this is the symbol, by the way, that astronomers use for helium, Y sub P. If you could see this expanded, you'd see that that's at 25%. That after a few minutes of the early universe, this complicated process going on here produced a universe that was still mostly hydrogen, but was 25% helium. and I can show you why 25% is the right number. We'll do that right now.
Why is there a peak at 2 minutes or something on most of those ratios?
Because, thank you, good question. This is a period when the neutrons, the free neutrons that were available to help build nuclei of heavy elements, was still fairly high. There was still enough neutron matter around. So you get this little bump, but by the time, as this process continued, the number of neutrons available to make heavier elements was depleted for two reasons. One, neutrons were being captured in nuclei to make heavy elements.
And they were just degrading.
And they were just degrading. So that's the last gasp for the neutrons, and then they drift down to zero. Okay, so let's go to this. This is very interesting. This will demonstrate why 25% of the universe is helium. So if you want to build helium, shown here, protons are little brown things, neutrons are gray. Let's start with 14 protons. And we add 2 neutrons. So these 2 protons and these 2 neutrons together form a helium nucleus. And there's electrons everywhere that can surround this nucleus, and we have a stable helium atom. What happens to these 12 guys? They're left over looking for another pair of neutrons. And so now we have, in this process, we started with 14 protons, 2 neutrons, and we have a leftover mass of 12 hydrogen nuclei. Remember, proton's a hydrogen nucleus, and we have 1 helium. So for every 12 for every 14 protons, we get 1 helium. And if you do the arithmetic, you end up showing that 25% of what results is helium. And in fact, when astronomers do surveys of, once again, that tedious thing of looking at galaxies and measuring the amount of helium and other elements, and then doing it for hundreds of millions of galaxies, you get 25% of the universe is helium. So by looking at how atoms are constructed, we can confirm what we see out in the universe. That's a simple form. All right, so here are the words on the right-hand panel. So for every 7 protons, let's do it again. For every 7 protons, we used a neutron. You have to go through the arithmetic and you'll see. So for every 14 neutrons, we get a helium atom, leaving 12 protons. And and the other important thing is the relative mass of protons and neutrons. So we get a ratio of 12 to 4, and that's what we see. So let's talk about what this looks like. So if you have a proton and a neutron arrives, you have a deuterium nucleus. And if another neutron arrives, that's a tritium nucleus. And that's a good nucleus for building lithium. But at the same time, this deuterium is also being consumed to produce helium-3, which ultimately can lead to beryllium. But when that happens, you get a neutron and a proton left over that go over and then this goes back that way, and it's just a jumble of equations all banging into each other. The early days of doing this in the late 1940s, early 1950s, this was a big challenge because computers didn't really exist. I mean, there were experimental computers, but being able to solve this kind of a problem in a computer in 1950 was pretty much out of the question. And this is why we have graduate students. So here are the equations. Now, it looks crazy at first, but let's go through it. Let's go through a couple of examples. Here's a neutron and a proton. A neutron. When it decays, it produces a proton, an electron, and this funny thing called a neutrino. And the proton when it collides with a neutron, can produce a heavy hydrogen nucleus. And you also see this symbol appears here, and here, and here, and here, and so forth. So if you link the equations together, then you get something that looks like this. So what's happened here is this proton-neutron got married and produced a baby deuterium, but the deuterium wants immediately to get married to a proton and produce helium-3, and this helium eventually makes a regular helium, and this helium wants to go over here and engage with the tritium, and this produces input for that, and so and this is what, seriously, this is what graduate students did. They figured out ways using arithmetic and analog computers to solve these problems. And they came up with distributions or predictions of the mass in the universe, and they did pretty well, except for lithium. Even the modern arithmetic of nuclear chemistry is having problems with lithium. And part of the problem is observational. Lithium was produced in the early universe, but it is also produced in stars. So when you go out to take pictures of stars and measure the amount of lithium in galaxies and so forth, you've got to have a technique, a reliable technique, for separating between what was produced in the Big Bang and what is the product of stellar activity that has occurred since the Big Bang. That is hard, but in working on this problem, a very interesting result was discovered. So, let me explain what we're looking at here. This is the prediction of deuterium, helium-3, lithium, based on modern understanding of nuclear chemistry, but it all depends on how much matter is in the universe, how much matter. Let's talk about what that means. We are made of matter. Stars and galaxies and people and trees are all made of matter. But what fraction of the entire universe is matter compared to other things? There are other kinds of material in the universe we'll talk about. Dark energy, dark matter. So when this nucleosynthesis drawing is first created, the question was, what fraction of the universe should we put in to see if our model for nuclear chemistry actually works? And you slide, this is what this gray bar is, you slide this around up here until these three curves best match what's been observed in nature by astronomers. And the best match is right here, somewhere between 4 and 5%. So that's kind of mysterious. Why is it that only 4 or 5% of our universe is made of atomic stuff? I call it us stuff, because we are made of atoms. It's the same stuff that's in trees and stars and galaxies. So this right away was kind of mysterious, because this is the place where our prediction for the amount of helium or deuterium actually matches what was measured. This horizontal orange bar is what was measured by astronomers. So what we were looking for is a place where this theoretical prediction from nuclear physics intersected what's measured by astronomers. And that intersection occurs right there. And if you go down, you get the universe is 4% atoms. Now, most people, perhaps most of you before this class would have said 100% of the universe is atoms. But it's not. So this is a first clue. There's something very interesting in cosmology about how the universe is structured. Now let's talk about lithium. This is the prediction for lithium as a function of how much of the universe is made of ordinary matter. And if you take these two intersections and say that must be the right place, right there, the actual measurement for lithium is here, the prediction's up here, and this is not a linear scale. That That's a factor of 5 in error. Not 5%, not 50%, but a factor of 500% error. And that's the mystery that's on the cutting edge of research, is to understand why doesn't our calculation of the amount of lithium from the early universe match what is observed by astronomers. As I say, this is complicated by the fact that this measurement has to take into account the production of lithium by stars. But nonetheless, that gap is mysterious. The bottom line for that slide is we have our first inkling that the universe is not entirely atoms. So I've highlighted the 4%. Now, there are people who are working on this, and this is a very recent, this is from 2017. Somebody has come up with a model. Here's the deuterium prediction in their model. Here's the helium prediction, and here's the lithium prediction. And see, they have another parameter they've introduced, and they think they have a solution to this dilemma about lithium, but it remains an open question. So, now this was on the front page of our lecture notes today. And here's the way to read this. This is the periodic table you learned in chemistry. This panel here, this color coding, tells you where the different elements came from. So let's read it this way. Here's helium, Big Bang, all the helium came from the Big Bang. Lithium is different. Some of it came from the Big Bang, because these colors match, but a lot of the lithium, maybe 15%, comes from cosmic ray fission in the atmosphere of stars, and a bunch comes from dying low-mass stars spew out lithium, so as in their dying progress. Beryllium is almost entirely from cosmic ray fission. Cosmic rays are highly energetic forms of light, really, the source of which is still a mystery. But you see, anywhere it's kind of a gold color, exploding massive stars. Gray, exploding white dwarf stars. We will talk about the different stellar types. Purple, neutron stars. So any of this stuff here, like most of the xenon in the universe, comes from neutron stars crashing into each other. And when you get down here, this right here, this panel right there, that's all human-made, americium, and so forth, stuff that's made in nuclear reactors. And its half-life is so short that if it's ever produced in nature, it's quickly gone. So this is the new model of chemistry based on where the elements came from.
Why is there a peak for iron in abundance?
Because a standard star like our sun can fuse elements lighter than iron and produce iron. That's the heaviest thing that our sun can produce. And our sun is a pretty typical...
The mainline star.
It's a main sequence star. So we should touch on this a little bit more, and we'll have a break. In the process of producing light in the interior of a star, fusion is going on. Hydrogen, like I showed you, hydrogen is fused into helium, and in that process, energy is released. When you get up to iron, if you fuse iron, it takes energy to fuse iron atoms together. So it becomes a sink of energy rather than a source. So our sun cannot produce anything heavier than iron. So there's exploding. The iron in our star will get thrown out into the universe if the sun explodes. Right now, they don't expect it to explode. It just becomes a big red giant and just cools off slowly over billions of years. Okay. Any questions?
What did you say the cosmic ray fission was?
The cosmic...
Ray fission.
Oh, cosmic ray fission. Okay, so fission is breaking. Cosmic rays are incredibly energetic.